Okay, good afternoon, and welcome to the final technical session of uASC'26 about memory. And our first speaker is Antoine Plin from the following institutions: ESILV, GeorgiaTech, and also CentraleSupélec, Inria, CNRS, and IRISA. Please.
Thank you for the introduction. So I'm Antoine Plin. I'm a master's student at GeorgiaTech. And I'm going to be presenting my work on DRAM address mapping reverse engineering that I did during my summer internship at Inria with Thomas, Lorenzo, and Ruben. So first, before talking about mapping, we have to know what we are mapping exactly. DRAM is a component that has different levels of hierarchy. So we have ranks, banks, and each bank is a grid composed of multiple rows and columns. Inside of each bank, there is a circuit called the row buffer, which serves as a cache that contains the last access row of the bank. And so opening a row means loading a new row inside of the buffer. And closing a row means putting back the data that was inside of the row buffer back into its original place in the bank. But as you can see, when you want to open a new row, you first have to close the previous one and then open the new one. And that induces more latency than accessing an address from a completely different bank. Moreover, DRAM, as other parts of the microarchitecture, is vulnerable to different attacks. The most famous one being row hammer, which is a disturbance-induced fault from high-frequency accesses. But it has been mitigated by target row refresh in newer LPDDR standards. But new variants emerged, such as half double and trespass, to realize the attack despite those mitigations. However, they have a common prerequisite, which is a knowledge of the DRAM addressing in order to craft complex access patterns inside of the same bank. So DRAM addressing is done by the memory controller, so somewhere between the CPU core and the actual DRAM device. And its goal is to take the physical address from the CPU core and to transform it into a tuple that represents the DRAM location. For this work, we'll make a few assumptions, such as uniformity, meaning that the physical addresses will be uniformly distributed to DRAM location. We make this assumption because manufacturers, we assume, will try to spread as much as possible the load on the memory. And we also assume that this mapping is done in a linear fashion. That means that it is done by using XOR operation on different bits of the physical address. So the question is, how do we get to this mapping? So the first software-only method was described in the drama paper. And it uses the row buffer side channel, which, as we've seen before, is that the sequential access to different rows of the same bank increases the access latency. So as you can see on this diagram, we have the peak highlighted in green that represent normal accesses, so which are with a lower latency. And in the blue box, we have a higher latency peak, which represent conflict. So it means that between the two addresses that we accessed were part of the same bank. However, this methodology had a few limitations. The first one being knowing the DRAM geometry to know exactly the type of functions that we are looking for. They also use the brute forcing of the XOR mask, which means that the complexity is exponential with address sizes, so it doesn't scale properly with as the size of DRAM grows. And it is also sensitive to noise because any noisy measurement might break the brute force search. Later works expanded this methodology by often by using trade-off between the speed and the platform agnosticity, for example, by using specific counters or on some specific generation of Intel CPUs. By luck, some previous work on cache addressing used algebraic functions and use linear techniques to reverse engineer the addressing functions. So our research question is, can linear algebra improve DRAM mapping reverse engineering? So to give a quick overview of our methodology, of course, we start with the assumption that the DRAM function that we are looking for will be linear. And so with this linear assumption, we can ground it into linear algebra. And in that case, function becomes matrices, and our addresses become binary vectors. So our methodology consists of the different reverse engineering phase, so the blue phase on that pipeline. So the first one is to retrieve the bank mask. So for this, we find a set of conflicting pairs, meaning pairs of addresses that produced higher latency access. We build a different matrix by XORing each pair of these addresses. Then we row reduce this matrix to basically get the essential of the information given by these different matrices. Then we find the null space of this matrix, and that gives us directly the different function used for the mapping. So you can see that in the first line we have a 1 at the first position, so it means that the function directly maps only the first bit, whereas the second row has a 1 on the second position, so it means that the mapping uses the second bit. However, to find the row functions, we use the same methodology, but that isn't enough because our side channel give us info for partitioning, right? Like only determine if two addresses map to the same location or not, but it doesn't give us any info on indexing, which is what we actually need for the attacks. So there is no way to get the real mapping function outside of the banks. So a way to do that is to use our reduced search space that we found from the previous phase and to restrict it using hardware assumptions. So the first one is basically that the bits encoding the row will be put sequentially inside of the physical address. We also assume that the mapping function will try to use as few XOR gates as possible inside of the hardware. And also that the function addressing the different rows will be linearly independent from the bank addressing function. This way we can preserve bijectivity, meaning that each physical address will map to one and exactly one physical location inside of the DRAM. And then we developed a backtracking algorithm to retrieve the most plausible basis by observing those different conditions. And from then we have a full row mask and therefore a full mapping to start attacks. So we tested this methodology on 10 different devices across 4 different architectures, including PowerPC, and on pretty sizable DRAM sizes, up to 512 gigabytes DDR5. I think the important part is also that we can see that our methodology works across different generations of DRAM, from LPDDR2 to So the main contribution of this paper is, first of all, that we reduce the worst-case search complexity from exponential to polynomial, since the complexity is now bounded by the Gaussian elimination that we use to find the null space. We also have a provable sample bound, which comes from the linear algebra grounding of this methodology. And therefore, since we don't use any new counters, it's also platform agnostic. However, it still has some limitations. The first one being that it requires an access to /proc/pagemap on Linux to retrieve the physical addresses. And this interface is full-fledged since Linux 4.0. However, it still opens a threat model where the attacker has an access to its own device. For example, in one of the tested targets, we had a Pixel 3a, so an attacker could reverse engineering on his own and then apply the found mapping to the victims. We also observed one case of closed page policy. It's a case where the raw buffer is actually not used, and therefore the side channel completely disappears because all DRAM accesses will take the same amount of time. Also, our methodology still rely on some assumptions. So even though we empirically verify them, it doesn't make them ground truth. And of course, for now, they only support linear functions. And if you want the complete details on the algebra we did or the source code, you can find them using this. Thank you.
Okay. Thank you, Antoine. We have some time for questions. While I'm walking up there, I'll ask you something. I saw that you had 99% success rate, yeah, and not 100%. So this is algebra, so it's kind of confusing to me. Can you maybe comment what is in that 1% and what is the root cause of that
Since
error?
the testing methodology is to pick different pair of addresses and test if our mapping might explain or not the conflicts or not that we observed, this 99% can also just be measurement noise, right? Because maybe our model correctly predicted a conflict, but because of noisy measurement, when using the measurement, we didn't see the actual conflict just because of noise.
Thank you very much for the talk. I was wondering whether you could basically adapt your algorithm to, instead of working with the full page map, work with huge pages where you have like 2 megabytes of aligned memory where you know it's physically consistent. Is that an option, or would that just not work with your algorithm?
What do you mean exactly by that? Running the methodology only using huge pages?
Yes, whether that can work using only huge pages. Well, because they are generally available and you get like physically consistent memory without privileges.
It might work, at least partially, right? Because we still don't have access to the higher bits. But yeah, normally it should work if the functions are contained inside of the bits that we have access to using huge pages.
But you would gain the information that the higher bits are equal in the huge page, so maybe that's...
I don't think so. I don't think you could get information on the higher bits. At least it's not something that we try.
I mean, you can get implicit information that
yes,
they're
probably.
like, because they're consistent throughout the huge page, right? It's
yes.
like one physical huge page, so you could get some information about it, just not very explicitly.
Thanks for the talk. One question, so you mentioned nonlinear functions. So we know that for caches, nonlinear functions appear when you have non-powers of 2 number of cache slices. Are there a system where it is known already that you have DRAM addressing functions that are not linear?
Yes, for example, on some AMD processors, the slides of physical addresses that are mapped to the DRAM are not continuous. And in that case, we can still put them back to approximate them by linear by finding where the gap is of addresses that are not linked to DRAM, but for example to MMIO. And then we subtract the size of this gap from the addresses that are on the other side. And then it restores linearity.
Final question for the speaker? So maybe because we have a few minutes, and if you could just give us a little hand-waving motivation of how null space, what is null space and why is it a good answer to this challenge of row mapping?
It is a pretty long proof.
Just intuitively, just on the slides, because it was fascinating to me that this jump. Oh no.
Yeah,
no.
So it's...
I regret that.
It is because of the properties of parity on addresses. And so by doing some binary operation, you can simplify the whole system to just a simple null space analysis on the matrix made of the differences between the different address pairs.
Simple indeed. Okay. So let's thank our speaker again. Thank you, Antoine.